In the next few minutes, I'll show you why every language model has a hard limit on how much it can see at once, why that limit ranges from 2,000 tokens to over 1 million depending on the model, why you can't just make it infinite, what actually breaks when you hit it, and why this single number, the context window, quietly decides more about how AI products are built than almost any other choice the engineers ever make. Welcome to Concept Stack. We produce one concept a day and each one stacks on the last, building the framework for AI together. Let's dive into context windows. Last episode, we walked through inference, how a model actually generates text. We ended with the KV cache, the trick that keeps long generations from getting quadratically expensive. But we glossed over something. Every forward pass attends to every token in the sequence, the prompt, the chat history, every token the model has produced so far. That sequence has to live somewhere, and it has a ceiling. The ceiling is called the context window, and it's the number that quietly governs every AI product you've ever used. A context window is the maximum number of tokens a model can see in a single forward pass. Everything the model uses to generate the next token has to fit inside it. Your prompt, the system prompt, every prior turn in the conversation, any documents the app retrieved for you, and the response the model is currently typing. They all share one budget. When the conversation grows past that limit, something has to give. Usually the oldest messages get silently dropped, or the API just rejects the request. Either way, the model can't see what's gone. Now here's the strange part. GPT-3 launched in 2020 with a context window of 2,048 tokens. Today's frontier models have over 1 million. Why such a wild range, and why don't they just make it infinite? Because attention scales with the square of the sequence length. In every layer of the transformer, every token attends to every other token. 2,000 tokens means 4 million attention comparisons per layer. 32,000 tokens means 1 billion. 1 million tokens means 1 trillion comparisons per layer. And a frontier model has 100 or more layers. Double the context window and you don't double the cost, you quadruple it. That's why context windows feel like they grow in leaps and stalls. Every doubling is a research milestone, not an engineering tweak. Infinite context isn't a product decision. It's a math problem nobody has fully solved. So researchers went after the constants. Flash attention was the breakthrough. Same quadratic math, but rearranged to fit GPU memory better. It made attention 10 times faster and used half the memory, and it's now standard in every modern model. Sliding window attention restricts each token to looking at a window of nearby tokens, which drops the cost from n squared to n times the window size at the cost of long-range recall. Ring attention and sparse attention split the work across GPUs or skip pairs that almost certainly don't matter. None of these fix the quadratic problem in theory. They just shrink the constants enough that 1 million token context fits on real hardware. And the field isn't done. Researchers are still chasing genuinely sub-quadratic alternatives. State space models like Mamba, hybrid architectures that mix attention with cheaper layers. But every approach so far trades something away, and none of them have replaced attention at the frontier yet. Hitting the limit doesn't always look like an error. The loud version is hard truncation. The API rejects the request and tells you, easy. The quiet version is what trips up real products. Chat clients drop old messages without telling you. The model answers based on a conversation it can no longer see, and the user just thinks it got dumber. Then there's a stranger failure called lost in the middle. Even when a fact is technically inside the window, models pay much more attention to the beginning and end than to the middle. Bury an important detail at the 50% mark of a long document, and the model often acts like it isn't there. The window gives you space. It doesn't guarantee the model uses it. There's a second cost the brochures don't talk about. Remember the KV cache from last episode? Every token in your context window has to live in that cache, in GPU memory, for the entire generation. A long context isn't free even if the math behaves. It eats VRAM in proportion to its length. A 70 billion parameter model at 128,000 tokens of context can spend over 300 gigabytes just holding the cache for one conversation. before it generates a single token of output, per GPU. That's why providers charge more for long context calls, and why self-hosting a long context model is a different machine entirely from self-hosting a normal one. Once context windows got large enough to fit a whole book, a real architectural choice opened up. Option 1. Just paste the whole document into the prompt and let the model handle it. Simple, no extra system, but you pay for every token, and lost in the middle starts to bite. Option 2. Use the vector databases we covered in episode 4. Search the corpus, retrieve the few chunks that actually look relevant, and inject only those. Cheaper. Scales to billions of documents. But if the retrieval misses, the model can't see the answer at all. A concrete way to think about it: fitting 100-page contract into a long context call works fine. Searching across 10,000 contracts to find the one clause that actually matters, that's where retrieval pays off. This is the architectural choice behind almost every AI product on the market right now. Most production systems use both. So where are we in 2026? GPT-4 Turbo runs at 128,000 tokens. Claude ranges from 200,000 to 1 million depending on the tier. Gemini 1.5 Pro ships at 1 million standard with a 2 million token experimental mode. 1 million tokens is roughly a feature-length book. On the open weight side, Llama 3 and Mistral Large hit 128,000, but most local models you can actually run on a single GPU sit between 8 and 32,000. The advertised number matters, but so does the quality at the high end. Many models claim a long window and then struggle to use it well past a fraction of it. Every benchmark that tests recall across a long context shows accuracy dropping well before the stated limit. So the published number is the ceiling, not the working zone. But here's the thing. Even a 2 million token window is small. A typical company's wiki is bigger than that. A legal corpus is bigger than that. The open web is many orders of magnitude bigger than that. So the question every serious AI product ends up asking isn't, how do I fit everything in the window? It's, how do I get the right things into the window? That's a different problem with its own name and its own architecture. And it pulls directly on the vector databases we covered back in episode 4. Retrieval Augmented Generation, RAG for short, it's how every AI product that touches real-world data actually works. That's the end of this concept, but each video stacks on the last. Subscribe, and we add the next layer tomorrow. Up next, RAG, retrieval, ranking, and the architecture that pulls vector databases, embeddings, and language models into one system. Thanks for watching.